Welcome to Lecture 6 on matrices. The topic is inverse of a matrix. I am your lecturer, Professor E.O. Efanga. Definition of inverse of a matrix. Let A be an n by n square matrix. If A is non-singular, then there exists a unique n by n matrix B such that A times B is equal to B times A is equal to I. The matrix B is what we call the inverse of A. And the inverse of A is usually written as A raised to power minus 1. So therefore, A times A inverse is equal to A inverse times A is equal to the identity matrix I. If the matrix A has an inverse, it is often said to be invertible. The inverse of A is given by the formula A inverse is equal to 1 over determinant of A times the adjoint of A. Inverse of a 2 by 2 matrix. Given a 2 by 2 matrix A with entries A, B, C, D. To obtain the inverse of A, first we have to find the determinant of A, and the determinant of this matrix A is A times D minus B times C. Having done that, the next thing we have to do is to compute the cofactors of each element of A. First, C11, that's the cofactor associated with this element A, is obtained by deleting row 1, column 1, and that will give us the minor D. Then C11 is equal to D, since 1 plus 1 is even. C12 is equal to minus C. That's we delete row 1, column 2. Since 1 plus 2 is odd, then the cofactor associated with B is minus C. C21 is minus B, and C22 is A. We can then form the matrix of the cofactor C, which is equal to D minus C minus B, C. Therefore, the adjoint of A, we recall, is defined to be the transpose of the matrix of cofactors. So transposing C, that will give us the adjoint of A equal to C transpose, which is equal to the matrix D minus B minus C, A. So therefore, the inverse of A is A inverse equal to 1 all over the determinant times the adjoint. Please note, for a 2 by 2 matrix, it is very easy for one to write down the inverse without passing through this process. All we need to do is find the determinant and then write 1 all over the determinant. Then the adjoint is obtained simply by interchanging these two. D will come here while A will come here, and then change the sign of B and the sign of C. Example 1. Let us find the inverse of this 2 by 2 matrix. Solution. First, we obtain the determinant of A. The determinant of A is 1 times 3 minus 2 times 4. And that will give us 3 plus 8, which is equal to 11. So therefore, the inverse of A is equal to 1 all over 11 times the adjoint of A. The adjoint of A, we recall, we have to interchange these two. So these 3 will come over here, while 1 will come over here. Now we change the sign of this. So this will become plus 2. We change the sign of this, and that will become minus 4. So that gives us the inverse of A. It is as simple as that. Now let us take an example on the inverse of a 3 by 3 matrix. Example 2. Find the inverse of this 3 by 3 matrix A. Solution. Let us obtain the cofactors of every element in A. First, C11 is equal to M11, and that is equal to minus 1. That is, when you delete row 1, column 1, you obtain the minor to be 0 times 0 minus 1 times 1, and that will give us minus 1. So C11 is equal to the minor M11, which is equal to minus 1. Similarly, we can compute C12 to be minus M12, which is equal to 1. C13 is equal to M13, which is equal to 1. C21 is equal to minus M21, and that is equal to 1. C22 is equal to M22, and that is equal to minus 1. C23 is equal to minus M23, and that is equal to 1. C31 is equal to M31, which is equal to 1. C32 is equal to minus M32, and that is equal to 1. And then C33 is equal to M33, which is equal to minus 1. Having obtained the cofactors of all the elements of A, we are now ready to form the matrix of the cofactors. And the matrix of the cofactors C is equal to this. Then the adjoint of A is equal to C transpose. Transposing this will give us this. Please notice that C is a symmetric matrix, so transposing it will still give us C. So next, we obtain the determinant of A using the cofactors method. To obtain the determinant of A using row 1, we have to multiply every element in row 1 by the associated cofactor. So in our A, the first element in row 1 is 0, so we multiply it by minus 1. The second element in row 1 of A is 1, so we multiply it by the associated cofactor 1. And the third element in row 1 of A is also 1, so we multiply by the associated cofactor, which is also 1. So 0 times minus 1 plus 1 times 1 plus 1 times 1 will give us 2. So the determinant of our matrix A is equal to 2. Therefore, the inverse of A is equal to 1 all over determinant, that's 1 all over 2 times the adjoint of A. Let us now look at the properties of inverse of a matrix. Property 1. If A and B are non-singular square matrices of the same dimension, then the inverse of AB is equal to B inverse times A inverse. Proof. Please note that to prove that B inverse times A inverse is the inverse of AB, we have to pre-multiply this by AB and show that it is equal to I, and also post-multiply this by AB and show that it is also equal to I. Once that is done, that proves that this is the inverse of AB. Let us see how this is done. First, let us pre-multiply by AB. B inverse times AB is equal to B inverse times A in bracket times B. That's applying the associative property of matrix multiplication. But A inverse times A is I. So this is equal to B inverse times I then times B in bracket. But I times B is B. So this will give us B inverse times B. But B inverse times B is equal to I. Next, we post multiply this by AB. Post multiplying this by AB will give us A times B inverse in bracket, then times A inverse. Still applying the associative property of matrix multiplication. But B times B inverse is I. So this will give us AI times A inverse. But A times I is A. And this will therefore give us A times A inverse. But A times A inverse is equal to I. So therefore, the inverse of AB is equal to B inverse times A inverse. Property 2. The inverse of A transpose is equal to the transpose of A inverse. Proof. Again, we have to show that pre-multiplying this by A transpose will give us I. And also post-multiplying this by A transpose will give us I. First, let us pre-multiply this by A transpose. That's the transpose of A inverse times A transpose is equal to A times A inverse transpose. Recall the reversal rule for the transpose of the product of two matrices. But since A times A inverse is I, this is equal to I transpose. I transpose is equal to I. Next, we post multiply this by A transpose. That's A transpose times the transpose of A inverse is equal to, again by the reversal rule for the transpose of the product of two matrices, this is equal to the transpose of A inverse times A. But A inverse times A is also I, so this is equal to I transpose. And I transpose is equal to I. So therefore, we have shown that the transpose of A inverse is equal to the inverse of A transpose. Property 3. The inverse of A inverse is equal to A. Proof. We have to show that pre-multiplying A by A inverse is I, and also post-multiplying A by A inverse is I. That is, A inverse times A is equal to I by definition, and also A times A inverse is equal to I by definition. So therefore, the inverse of A inverse is equal to A. Property 4. The trace of A times C times A inverse is equal to the trace of C. Proof. We recall that the trace of the product of three matrices is cyclically permuted. That's the trace of AC A inverse is equal to the trace of, you bring the A inverse backward, that will become A inverse A, then times C. But A inverse times A is equal to I. So this is equal to the trace of IC. I times C is equal to C. And this will give us the trace of C. On your own, find the inverse of the following matrices. 1. This 2 by 2 matrix. 2. This 3 by 3 matrix. And 3. This 3 by 3 matrix. We have come to the end of our lecture 6. Thank you for watching, and keep on watching.